As an introduction, my name is Kevin Lawson. I'm a professional engineer. I've got about 12 years of experience in consulting engineering, designing buildings, and I left about 2.5 years ago to found Ripple, and we make the Ripple HVAC Toolkit, and we're going to demonstrate two features of that today. But first, we're going to talk a little bit about the toolkit. It's not just chiller and boiler plant selections. We've got a whole suite of tools, and the Ripple HVAC Toolkit is free to you. It's sponsored by manufacturers. So you could head to my website at rippleengineeringsoftware.com and hit download now to get it and install it. It just comes in an installer, or you could go to the Autodesk App Store right here, and you can install it from the App Store. The other features it comes with heating and cooling loads, automated diffuser selections and layouts, auto zoning and VAV auto selection, an AHU configurator, and now a chiller and boiler plant configurator, and that's all wrapped together with an easy button. And the data flows forward. So the heating and cooling loads, they flow forward into your automated diffuser selection, and your VAV selections and your AHU selections, and now that data is going to flow forward into your chiller and boiler plant selections. And I'll show you how that works in a second. If you'd like to learn more about these features, there's an hour-long webinar on each topic that you can go to, and you could learn every detail about every feature here. Okay, but first, so for the chiller and boiler plant selections, let's first talk about what this is going to drop in. So here are some examples of what this is going to drop into Revit for you. Air-cooled chiller, water-cooled chiller plant, and a boiler plant. And the intent here is to follow ASHRAE Guideline 36, figure A14, variable primary chilled water plant. So this is the flow diagram we've got in mind when we're dropping this equipment in. And this is helpful because the sequences for these plants, you could just go to ASHRAE 36 and you've got a sequence written and it works with these arrangements. Same goes for the boiler plant. This is figure A23. So again, variable primary, a pump to each boiler. You've got a sequence ready to go. You just got to go to ASHRAE 36. We haven't picked a basis of design manufacturer for this equipment yet, so we're just kind of making generic selections here, and the intent is to start carving out space in the architectural model so that we could do that quickly and early in the project, so it's easier to get space for some of this equipment. But to get some generic equipment in here, we're using Carrier Aquaforce for air-cooled chillers. We're using Trane Centrovacs for water-cooled chillers. We're using Baltimore Aircoil for cooling towers, Airco for boilers, and Bell & Gossett for pumps, expansion tanks, and air separators. But let's get into Revit and see how this all works. Okay, so once you've installed Ripple HVAC Toolkit, you get a new tab up here. It comes with all of these features. So we're going to be focusing on these two features here now, but again, load calculations, air terminal layouts, VAV selections, and then the easy buttons over here. I want to point out that if you want to go to the webinars, you could also go from the help button, and if you want to download the white papers on how this works, you can download them here. So there's validating BIM load calculations, diffuser selection and layout, zoning, VAV selections, and all of that helpful information is right here. So this is, the default Revit project. It's a school. I've already hit the easy button on it, so we've already selected VAVs, we've selected air handling units, and now we're going to open up the chiller plant configurator and see what see what this looks like then. So it's, if you use the Ripple HU configurator, it knows to go to these families and what parameters to look at to pull in this information to get the loads. It then sums those loads up and says, okay, hey, we're going to size this based on this is the total load in the project that we're getting at. Now, all of these values are overridable, but by default, it's gonna have default values selected for all this stuff. So you can just select an insertion point and hit select plant, and you've got, you know, kind of the default plant ready to go for you. This is the air-cooled plant. So for this project, it's going to say I've got 341 total tons, max chiller size is 500, and I want a little bit of redundancy, 67% redundancy. So it's going to tell me, hey, you need 2 circuits, and you at 228 tons per circuit gives you 67% redundancy. Now, when it goes and drops the chiller in, it's basically just going to use nameplate data to select the chiller. So it needed 228. It had the option between 220 and 240, and so it dropped into 240 here. Again, all of this stuff is overridable. So let's say that I wasn't using Ripple HUs, or let's say that this was an existing building and we're putting a new plant in and we're going to backfeed an existing building. So we could put that in as a load. And let's say all those coils were sized for 10-degree delta T. So we're going to put 52 in there, and let's say that's 1,000 tons. So it's going to calculate what my new tons are, and it's going to calculate my new return water temperature too, so that, you know, when all this water gets mixed together, it's got a new return water temperature. And then we could override this stuff too. So maybe at this tonnage, we're going to go water cooled. So let's jump over here to the water cooled tab. Now my max chiller size for water cooled is 1250. So at same redundancy 0.67, it's telling me I need 2 chiller circuits and at about 900 tons. So let's select the insertion point, move this over, and it's going to drop in 2, 910 ton chillers. Let's say we want some more redundancy here. Let's say we want N+1. So now that's going to give me 3 at 670. Go here, select the water cooled chiller plant. So that's giving me 3 at 670. Let's say I know that I want 4 at 500. And I can just ignore all of this. Select the insertion point over here and drop these in. So you could just really quickly get this stuff dropped in and start getting sizes paired out for it. And it's all overridable. Now, notice that we're not putting in any piping. There's no piping and there's no piping specialties. The goal is, as we bring on manufacturers and get real selections for all of this equipment, we'll start adding piping and piping specialties. And really the goal is to put these all on a skid so that they could be prefabbed and just shipped out as kind of one piping piece. So that's the goal there. So that's how you get the chiller plants into the model, and the boiler plants work very similar. Now for the boiler plants, that data feed forward is a lot more valuable because you've got air handling units and VAVs. So you've got all of these VAVs here that are kind of hard to keep track of. But again, if you use the VAV auto select, it knows what parameters to look for to pull the right information in. Just like the chiller plant, all of this stuff can be overridden, but for this building, it's telling me I need, 2,400 MBH, and it wants 75% redundancy, so it's telling me I need 2 at this. We're gonna go ahead and select the insertion point to be down here, and we'll select the heating water plant. And that just drops that in. Just like anything, you could do the N+1. Or you can even do, hey, I know I want 3 circuits at 5. Let's do 3 at 1,000. Put that over here. However you want to do it, but it gives you default values here for the for everything. Again, just like the chillers, it's just size on nameplate information that will be improved, but for now we want to start carving out some size. Let's look at how the rest of these, how we're sizing pumps and expansion tanks and cooling towers and all that good stuff. So here are the cooling towers. Here's everything I just dropped in 3D. Okay, first let's talk about kind of load. When we're sizing these plants, what are these values? Where do these values come from? So first thing we need to do is we need to meet the load. So that's where the load pulls through. We need to come up with, economic manual manufacturing sizes. So, they don't make 10,000 ton chillers. So you have to limit the size to something reasonable. And that's typically something that fits on the back of a truck. You want to provide some redundancy. That a little bit of redundancy in HVAC can go a long way. So 2 chillers or boilers sized at 67% might give you full redundancy for 90% of the year, just because you don't see those peak loads very often. And then providing multiple circuits gives you better turndown. So if stable turndown is typically 20 to 30%, so if you have 2 sized at 50%, you can really get like 50% turned down to the peak load. So that's why those values are there. And a lot of times owners will have kind of default values they want to see for the redundancy and the sizing. So for example, the VA, they say, hey, don't exceed 1250 tons within any single water-cooled chiller. They want a minimum of 2 chillers. GSA wants 2 chillers sized at 66% load, or 3 chillers equally sized with no spare capacity. So it allows you to input that information and change it. Now these water temperatures are picked in the air handling unit configurator, but just for recall, that this comes from ASHRAE 90.1, which wants 15-degree delta T at minimum of 57-degree leaving water temperature. Again, heating water temperatures are picked at the VAV auto select or the AHU auto select, but again, we want those low as possible because the efficiency on those condensing boilers gets so high, the lower you've got that return water temperature. So that's why we're picking those low. Okay, the next thing you'll see is the cooling tower selection parameters. So 95, 85 is pretty standard for inlet and outlet condenser water temperatures, but the thing you got to pick is the outdoor air dry bulb and the outdoor air wet bulb. And where that's going to come from is Ripple is going to look at the site location. It's going to find the nearest ASHRAE weather station, and it's going to grab this evaporation wet bulb and mean coincident dry bulb, and that's what it's going to put right here. So 85, 75.1. For air cooled, you're more concerned about the dry bulb. So it's going to look at that cooling dry bulb, and it's going to add 5 degrees to account for the heat island effect of the roof or buildings or parking lots nearby. So it's going to be a little bit higher than what the cooling dry bulb is. Again, these values can be overridden as you see fit. And then those cooling towers are going to be selected based on minimum efficiency requirement. So it's going to pick a box size that gives you something greater than 40.2 GPM per fan horsepower. So that's how we're going to start carving out cooling tower sizing. Okay. Pumps. Now, pumps are a little bit harder to select. There's a lot more factors that go into selecting them. So what we're doing right now to start sizing those pumps is you have a box where you could put the external head, but it's always just going to assume you've got 60 feet of head, and it's going to pick a pump size basically on this line from this chart. So anything under 100 GPM, it's going to pick a 1.5 by 9.5. Anything under 150, it's going to pick a 2 by 9.5. Anything under 250, it's going to pick this. So it's kind of a blunt way to get a generic pump size in there, which again, once we bring on a manufacturer, we'll improve this a lot. But here's where that information comes from. Collapse these loads. The last thing is expansion tanks. So this actually has the most input, and people think expansion tanks are the simplest. But how we're going to do this is, first, to size an expansion tank, you need to know the heating water volume. And to do that, you have to have all of the pipes sized and routed, which you're not going to have at the beginning. So we need a way to estimate this volume, both for heating water and for chilled water. So I was researching ways to do that, and I found in the Amtrol reference book, there's a good way of estimating the volume given the building. But even then, you might not have even the building. Like if you're backfeeding an existing building that's not modeled, you might not have those dimensions. So I came up with a way of basically taking the load, getting it back into a square footage, and then taking kind of a characteristic length of the building and estimating the chilled water volumes from there. So this number for system volume is going to be a wild guess, but it's going to get you in the ballpark of what you need. Water temperatures are going to come from your heating water supply temperature. We're going to assume you're filling with groundwater. The max elevations and the min elevations actually are going to come from the families that these loads are on. So the highest air handling unit, or VAV, we have in the model is at 37.4 feet. So that automatically gets pulled in. We've got min elevation of 0 because that's where the boiler plant's going in. And so we're going to calculate the fill pressure here. And that's basically the height divided by the density of the fluid with 5, and then add 5 PSI at the end of that. And so here's that fill pressure calculation right there. Max allowable fill pressure, and that's going to calculate the tank acceptance volume. And then that's calculated from here. And then we're going to be able to size a tank from that. So that's how that equipment is selected. So all of these inputs are overridable. It's just that they are going to have default values, and those default values are going to be used when we hit the easy button, or when an architect uses the engineering on demand tool. So the default values and the default selections, especially for air-cooled or water-cooled, is what we need to dig into a little bit more. So when do we select water-cooled and when do we select air-cooled? So we're going to talk about that first. I'm going to jump into the questions to see if there's anything about how this interface works. Okay. Okay, schedules. So the question is, does it come in with schedule data filled out? Not yet. So that is something that as we bring on manufacturers, we'll add real schedules and better schedules. But for now, I just wanted to get the sizes and stuff in there. But that'll be upcoming in a future release. Okay. So in both of these, are there specific shared parameters that it looks for? So the question is, the question is, when you open these chiller plant configurator, where do these parameters come from? And yes, they are specific shared parameters that they look for, both for the chilled water and the heating water. So if you don't use the VAV auto select or the HU configurator, this is going to come in blank and you're not going to have any loads here. These will only be automatically filled out if you use these tools. And that's because, yeah, I got to know what parameter maps to what field. And so if you're using some family that I don't know, it's not going to fill that in. If that is the case, you can always just, even if none of these go out, you have to go in and manually add your own chilled water loads. If you know what the building is or what you're expecting for the building, you could just put that in here. But that's a good question. It only works with Ripple supplied families, which would be price VAVs. And right now, again, this is just a generic air handling unit. Okay, will you be able to send us a recording and the PowerPoint? Yes, absolutely. SI units, so all of my user interfaces are going to be in inch pound. So you'll just have to convert back and forth when you're using my user interfaces, but it will read the data from whatever units you have set for the project, and it'll put that information back in. Once the basis of design are selected, will details also be added? That, yes, as we start getting like true actual selections, we will just add up to fabrication level detail of how exactly all of this stuff is assembled. Okay, another question about the parameters. I currently don't have a way to use any other families other than the price VAVs and the Ripple air handling units. I'd have to think about how to get how to integrate for something else. So if you're using anything other than the price VAVs, you're going to have to just manually figure out what the load is from a spreadsheet or whatever that is and type that in. Next question about glycol in the chilled water. I don't have that now. It will probably be something that's added in the future. We have glycol for heating water, but not for chilled water. That's something that I could add in a future release, though. Okay. That is all of the questions we had so far. Okay, so let's get back in to when to choose air cooled and when to choose water cooled and when to choose DX, and how are these default decisions going to be made with the easy button and with the engineering on demand product. So before we get into why, let's just get into what. So the easy button, if you hit the easy button and the total project load is less than 100 tons, it's just going to put DX on the rooftop units, on the air handling units, essentially. If it's less than 500 tons, it's going to give you air-cooled chillers. And if it's greater than 500 tons, it's going to give you water-cooled chillers. On the heating side, if natural gas is available, it's going to put a gas burner in the air handling unit. If it's greater than 1500 MBH, it's going to give you a heating water system. So you might hit the easy button and none of this is used, and you don't have any hydronics in the project at all. So if you're less than 100 tons and less than 1500 MBH, you're just going to have an air handling unit, and it's going to be assumed that all of the cooling and heating is going to happen inside that air handling unit. So for heating, that's basically just comes down to redundancy and lifetime, the life of the system. So hot water boilers, you can add redundancy pretty easily just by adding, multiple boilers. Whereas putting a gas burner in a air handling unit, that doesn't offer any redundancy. As soon as you get a hole in that burner, that whole unit's down, and there's no redundancy. So the bigger the building, the more you want redundancy, because you don't want 1,000 people having to go home from school because you've got a hole in your burner. So that's the decision here. The cooling source is a lot more complicated of a decision. And let's just review what those options are really quick. You've got DX, air to air. You've got air-cooled chiller, which is air to water. And you got a water-cooled chiller, which is water to water. They all have their pluses and minuses. DX systems are very cheap to install. You're already setting the air handling unit. The cooling equipment just comes with the air handling unit attached. It's already piped. It's quick and cheap. The problem is it's got very high energy costs. Air-cooled chillers are a little more efficient, and then water-cooled chillers are the most efficient. Water-cooled chillers have water costs associated with them, and they've got higher maintenance costs to deal with that condenser water system. They last longer than the other two, and both water-cooled and air-cooled, it's easy to add redundancy. Now, most of these are just hard costs that we could try to put dollar values to. And we're going to do that in a second. But there's some criteria that just kind of make your decision for you. One is space required, and one is acoustics. Sometimes you just don't have the space to fit a air-cooled chillers in. So here are two 500-ton unit space, and this is for the outdoors. So if you don't have the space to fit this, you have to go water-cooled because it's smaller. So that might just make the decision for you regardless of what the costs are. The other thing is acoustics. So if you're doing DX, that compressor is sitting right on top of the ductwork, which is like a conduit of noise to your spaces, which is where you don't want it. With an air-cooled chiller, you can move it to wherever you want it, but it's still outside. So you've got a compressor that's noisy that's outside, and that might cause problems with the property line. With water-cooled chillers, you can put them inside, put them in a big brick building, and they can be pretty quiet. Cooling towers can still be noisy, but they're way less noisy than a compressor on a air-cooled chiller. So those might make the decisions for you right there. But if they don't, if it's a standard building and you've got some options, you need to compare these costs. Now, ideally, you would run an energy model and a cost estimate for all three system types on that specific building. But that is not realistic. You probably don't have the time to do it. If you did have the time, you don't have the fee. And if you had the time and the fee, you don't know what the building is by the time you need to make this decision. Like the architect probably doesn't know what glazing he's using, but you need to know what the mechanical rooms look like. So it's kind of a chicken and the egg problem of you don't really have the information you need. So we need to get some baseline, kind of some baseline decisions made. So every building is going to have some sort of load profile. You know, lots of cooling load in the summer, a little bit of cooling load in the winter. Every building is going to be unique depending on what glazing they're using, what's the building orientation, what's the occupancy like, all of that good stuff. And again, ideally, you'd make this for your specific building, but we need a kind of a default building. And if we look at HRI 550, this is what they use to rate equipment. So they rate the part load efficiency, and their assumption is that, hey, you're only going to spend 1% of the time at 100% load. You're going to spend 42% of the time at 75% load. You're going to spend 45% of the time at 50% load, and you're going to spend 12% of the time at 25% load. So this 25, 50, 75 hours in the year, this is kind of the load profile that they are assuming, which I think is as good as any to get kind of a generic load profile for a building. And if you assume this load profile, for every ton you have installed, you're going to have 8760 hours times a ton times 12% times 25% plus, again, 8760, 45% of the time at 50%. And you're going to end up with 5,080 ton hours per ton installed. So that's like 61 million BTUs. So for every ton of cooling installed, assuming this load profile, you're going to be using 61 million BTUs of energy. Okay, now let's get that converted into a dollar value. So first we need to know equipment efficiency. So if we look at the IECC, we can see condensing units, 11.8 IEER, air-cooled chillers, 13.7 IPLB, and water-cooled, 0.5 IPLB. So if we convert these all to kW per ton, DX, we get about 1.12 kW per ton. Air-cooled, we get 0.876 kW per ton. And then water-cooled, to try to get it closer to apples, we have to add in some cooling tower and condenser pump, kW per ton. But let's say it's 0.65 kWs per ton. So you got that kW per ton times your energy use per year times your average kWh cost. So in the US, that's about 16.8 cents per kWh. And that is for DX, for every ton you have installed, you're probably spending about $960 per ton. For air-cooled, you're probably spending $750 per ton. And for water-cooled, you're spending $550 per ton. So as you can see, you might be spending twice the energy cost if you're using DX as if you're using water-cooled. And as we'll see, this ends up being by far the largest driver of your costs for any cooling plant is this energy cost. Water costs, DX air-cooled uses no water. Water-cooled uses about 1.9 gallons per ton hour. The average water rate in the US is about $2.50 per 1,000 gallons. That ends up being $23 per ton installed. So way, way, way less than your energy. So your water costs are just a fraction of what your energy costs are going to be. We've also got maintenance costs. Water-cooled maintenance costs are a lot more because you've got a condenser water system to maintain. Air-cooled and DX are a lot less, cleaning the fins and things like that. But here you've got to punch tubes, you've got chemical treatment, you've got all kinds of stuff with water-cooled, so it's a lot more expensive. All in all, it comes down to about $1,000 a ton for DX, about $750 a ton for air-cooled, and about $600 a ton for water-cooled. So now we need to compare that to the installation costs. Now, like everything in construction, installation costs of this stuff, it's kept close to everybody's chest. No one really likes to say how much any of this stuff costs. But from my experience, these are general rough numbers of installation costs per ton given DX, air-cooled, and water-cooled. This is going to be highly regionally variable. It's going to vary from year to year, project to project. If anyone thinks they have better numbers on these, I'd love to hear them. But in general, this is about what I think this stuff costs. You'll see as the tonnage goes up, the cost per ton goes down, which makes sense. Like it doesn't matter if you're installing a 200-ton chiller or a 1,000-ton chiller, you still have X amount of piping connections, X amount of equipment to place. You know, the stuff gets bigger, so it still costs more, but cost per ton go down. So this is what we're assuming here. So a 50-ton DX, 35,000. A 750-ton DX is 500,000, where a water-cooled is $1 million and an air-cooled is somewhere in between there. So if we break all this out and we go to a 5-year total cost of ownership, well, first let's look at the installation costs and the recurring costs here, and you can see that for DX equipment, you are spending on the first year, you are spending just about as much on energy as you are the installation costs. It's definitely not as bad for air-cooled or for water-cooled. These are more expensive up front and they use less energy. But the energy costs are really your number one cost here. So if we do a 5-year total cost of ownership, basically this plus 5 times this, you'll see at 50 tons. Well, first of all, it's hard to get a smaller air-cooled chiller, but DX and then air-cooled at 250 tons, air-cooled is still lower than water-cooled for total cost of ownership. But at 500 tons, that starts to flip. So it starts to be cheaper for a 5-year total cost of ownership to own a water-cooled cooling system than an air-cooled. And this makes sense with what gets manufactured. Typical air-cooled chiller ranges go up to about 500 tons. Water-cooled chillers don't go as small, and they go up to, you know, as big as you could kind of fit on the back of a truck with one compressor. So that is why Ripple is making these decisions. And as we dig in and bring on manufacturers and get better estimates of these costs, these values are subject to change. And ideally, we will be making a load profile chart for this for anytime you hit the easy button, it'll run an energy model and it'll give you a chart that looks like this. And it'll, you know, you can select, hey, we've got a owner that's more sensitive up front, so we're gonna pick DX, but it'll tell you the total cost of ownership. So that'll be a feature that'll be coming as we go, but we need to get real efficiency curves in here first. So that's the goal there. Trying to see if I missed anything. I'm sure I did. As always, if you guys have any questions, you have my email address. You can also always email support@rippleengineeringsoftware.com. But yeah, I'm going to go into the questions and see if we have any more questions now. Yeah, so the question is about the sizing portion. Is it the sum of peaks? And yes, that's exactly right. Let me share my screen here. What the easy button is going to size and what it's going to size the sum of peaks on the air handling unit. So it's just going to add up the load on all the air handling units, and that's the load it's going to give you. For the easy button, my kind of theory here is we're not taking any factors of safety anywhere in the model. No factors of safety on walls, windows, R values, U values, no factors of safety on load, no factors of safety on airflow, no factors of safety when it comes to equipment sizing. but we're also not going to take any diversity. We're just going to do sum of peaks. So what I've typically found is those things kind of cancel each other out. If the engineer is taking a reasonable factor of safety, the problem that I always see is that somebody takes a factor of safety on the U value, and then the engineer that looks at the airflows takes a factor of safety on the load, and then whoever sizes the equipment takes a factor of safety on that, and then the equipment just gets way too big. So taking a little bit of diversity after you took, 5 factors of safety isn't very helpful. So the goal is everything should be trackable. This load corresponds with this piece of equipment size. So that's the goal there. But yes, short answer is it's the sum of the peaks. If you have a different diversity, or if you have a different load that you want to hit, so hey, maybe this is 1,000 tons or 1,300 tons, but I know with diversity it's only going to be 1,000 tons. You could just type that in there and get a new chiller plant selection pretty easily. Does the program calculate 8760 loads or even just monthly loads? No, not at this point. At this point, it just calculates the peak load. Once we start getting equipment efficiency curves in here, then we'll start getting into modeling and giving you, the actual load profile of the building and the energy cost for that. But in my opinion, if you don't have those efficiency curves, if you can't break it out into a cost, it's not as useful. So I'm waiting to get until we get to that point to start integrating, systems analysis and the energy modeling energy modeling portion of it. Michael Bird asks, are manufacturers lining up to be integrated? Yeah, we're making good progress on that. If you have a manufacturer that you would like to see, somebody that you use, I mean, if you use them, it'd be very convenient for you if they were in Ripple. So send them my way. If you want to see a manufacturer in the tool, especially when it comes to chillers, boilers, pumps, and piping specialties. Another question about derate factors for glycol on chilled water or ambient roofs. Yeah, so again, we need to add glycol into the chilled water, and then once we're integrated with the manufacturer, yeah, we'll make an actual chiller selection with the amount of glycol you pick. The derate for and the derate will be accounted for too, based on what you put into here. So again, by default, this outdoor air dry bulb that we're going to select this air cooled chiller on, it's going to be 5 degrees above the 0.4% cooling dry bulb. So if you want this to be 115, you're going to have to manually change that to 115. But if you're in Miami and your 0.4 is 105, this is going to come in at 110. So it'll size it based on where the project is, where the Revit project is. Slides. I'll email everybody a PDH certificate, slides, and a link to the video, probably this week, today or tomorrow. Matt's got a question about loads. Is Ripple still using the Revit heating and cooling loads, or does it back in Energy Plus like systems analysis? So yeah, the easy button is going to use the heating and cooling loads tool in Revit. My plan is once we start getting equipment efficiency curves in, then we'll do the systems analysis and back into Energy Plus that way for the energy model, and then for another load calculation, so you can compare the two. But I think just running, if it's automated, you should just run both. I think that's all of the questions. If you have any more, feel free to email me. And again, I'll send you everybody emails with slides, PDH, and a recording. But looks like we're a little bit early. I thought I had way more. I thought that was going to take a lot longer, but it looks like we got done a little early. So enjoy lunch. Thanks, everybody.